Kia ora. In these first few videos, we're going through some preliminary content that you need for your study of abstract algebra. This is going to be the final one in this series, and it's going to cover a variety of facts about integers. So talking about things like divisibility, greatest common denominators, and some prime numbers. So we're just going to survey these ideas. We're not going to go through proofs of these things. It's definitely worth, if you've got some time, looking these up, but we're just going to go through the ideas and just sort of try them out with some examples. So let's get into it. We'll start with two integers a and b, and what we want to do is to divide a by b. Just to simplify things a bit, we're going to assume that b is greater than 0. We can easily adapt our results for negative values of b afterwards. So there are two main cases that we need to consider, or two things that can happen here. The first one is that the number a is actually divisible by b. So let's just throw up a quick definition as to what we mean by divides. So if I've got two integers a and b, with b being non-zero, we say that b divides a, or b is, in mathematical notation, we just use a little vertical line to indicate divides, if there is an integer q such that a is equal to b times q. That integer q, that's called the quotient. For example, 3 divides 12, because 12 can be written as 3 times a quotient of 4. Likewise, 4 divides 0, because 0 can be written as 4 times 0. The quotient in this case would be 0. And finally, 3 does not divide 7, because I can't come up with a quotient that makes that work. Which leads us to case 2. What happens if a is not divisible by b? Well, in this case, there'll be a remainder, which we'll call r. So our expression will look something like a equals b times q plus r, where the remainder r will be between 0 and b. So if we were dividing 58 by 7, we'd have 58 is equal to 8 times 7 plus 2. So the quotient here would be 8, and the remainder is 2. And you notice that 2 is between 0 and 8, not including 8. So these two cases can be put together into a single important theorem that we'll actually end up using in this course surprisingly often. And the theorem is called the division algorithm. And it goes a little bit like this. So let a and b be integers with b positive. Then there exist unique integers q and r, that's our quotient and remainder, such that a equals bq plus r, with 0 is less than or equal to r is less than b. So this is unique, and there's only one way you can do it. We're not going to prove it in this video, but let's try it out with some numbers. So just to try it out with something different, we'll try it out with a negative value of a. So let's try it with a is equal to negative 8, and we want to divide that by 7, so b equals 7. So the way to do that is we start with negative 58, and the way I like to think of it is we're going to add on 7s until we end up with a value between 0 and 7. That will be our remainder. So you can see here that you need to do this 9 times, because negative 58 plus 9 times 7 gives us 5, which is between 0 and 7. And if we rearrange that slightly, it's in the right form. So negative 58 will be negative 9 times 7 plus 5. So here our quotient is negative 9, and our remainder is going to be 5. So that's the division algorithm. Now, when we're working with integers, the concept of the greatest common divisor, or the GCD, sometimes it's called the highest common factor, or HCF, is going to come up quite a lot. So we'll start by just defining what this means. So first off, the greatest common divisor of two non-zero integers a and b is the largest of all the common divisors of a and b. So in mathematical notation, we write this as GCD of a and b. Now if the greatest common divisor of the two numbers is 1, in that case we say that a and b are relatively prime. They have no common factors apart from 1. So first off, the GCD always turns out to be positive, so you can always assume that. So let's look at an example of two numbers that are relatively prime. 8 and 9 are relatively prime. Their greatest common divisor is 1. They have no other factors in common. Let's look at another example where they're not relatively prime. So the greatest common divisor of 28 and 20 is actually equal to 4. Now how did we get this? Well, one way is just to look at it for a wee while, but there's also an algorithm that lets us find this reliably, which is called the Euclidean algorithm. Now, the Euclidean algorithm just works for positive a and b, but again, you might want to think about how you could adapt this to work with negative numbers. So here's how it works. For the Euclidean algorithm, we start with our two numbers, and we order them biggest to smallest. So we use the division algorithm to divide the larger number a by the smaller number b. So that will give us a is equal to b times q plus r. We then do another step, and we make our new a the old b, and we make our new b the old r, and then we do our division algorithm again on that new a and b. So for our example, the first line, 28 will be a and 20 will be b, gives us 28 is equal to 20 times 1 with a remainder of 8. We then take the b that we had before, which was 20, that's going to be our new a, and the r that we had before, which was 8, will be our new b, so we're going to divide 20 by 8. So 20 will equal 2 times 8 plus 4, and then we do it again. So now the new a is going to be 8, the new b is going to be 4, so we'll get 8 is equal to 2 times 4 plus 0. Now when we get a 0 remainder, we stop. And the GCD is the last non-zero remainder that we encountered. So for us, it is 4. That tells us the GCD of 20 and 28 is going to be equal to 4. It turns out that we can express the GCD of two integers a and b as a linear combination of them. So that means that the GCD of a and b can be written as a times s plus b times t for some integers that we need to find, s and t. So let's try it out on the example from before. So we know that the GCD of 20 and 28 is 4. So if we want to write it as a linear combination of 20 and 28, that means we're going to try and write down 4 is equal to 20 times s plus 28 times t. We need to find out what s and t are. We can actually use the Euclidean algorithm again to find this, just a little bit differently. So we're going to start from the top row, and at each step we're going to rearrange the step of working we did before to make the remainder the subject. So our first row is going to be 8 is equal to negative 20 times 1 plus 28. You can see that that 8 there is actually written as a linear combination of 20 and 28. It's in the right form already. Now we move down to the next row. This is the one that has our 4 in it. So this is going to be where the money is. So 4, rearranging it to make 4 the subject, the remainder of the subject is going to be negative 2 times 8 plus 20. But if you think about it for a second, we actually have an expression for 8 in terms of 20 and 28 that we can substitute in. So that will give us negative 2 times 8, which is negative 20 times 1 plus 28, plus 20. And now it's all in terms of 20s and 28s. So don't be tempted to actually do any multiplications here. Just keep it in terms of 20s and 28s. And that will give us 3 20s minus 2 28s. That's our linear combination that we're after. And if it was a slightly more complicated problem with more steps, it just works the same way. You just need to keep track of what you've substituted where, and in the end, when you get to your last row, you should have everything in terms of your original a and b. It's worth pointing out that the linear combination is not unique, unlike some other things we've been looking at. So another possibility would be 4 is equal to negative 4 times 20 plus 28 times 3. So there's a theorem about this, and it says it's actually slightly stronger than what we just said, because it turns out you cannot actually make a smaller number out of 20 and 28 than 4. 4 is the smallest you can get. So our theorem is that for any non-zero integers a and b, there exist integers s and t such that the GCD of a and b is equal to as plus b times t. That's our linear combination. And moreover, that means just in addition, GCD of a and b is the smallest positive integer of that form. You cannot make a smaller one. So we're not going to prove it in this video, but it does involve the well-ordering principle and the division algorithm. Now, there's one case that occurs so often that we'll actually give it its own result or its own corollary in its own right. So corollary just means kind of like an immediate consequence of a theorem. It's maybe a special case that's of so much interest that it's worth stating on its own. So our corollary is that if a and b are relatively prime, that means their GCD is 1, then there exist integers s and t such that as plus bt equals 1. So for example, we saw before that the GCD of 8 and 9 is 1, and so we can write 1, that's the GCD, is equal to negative 1 times 8 plus 1 times 9. Notice that the theorem itself doesn't give us the method of finding s and t. The way to do that is by the Euclidean algorithm like we just talked about before. Okay, moving on through our whistle-stop tour of integers. The last thing we want to talk about is prime numbers. And I'm going to state a couple of facts about these. So first off, what is a prime number? Well, an integer p, 2 or greater, nothing less than 2 is prime, is a prime number, or maybe just say is prime, if its only divisors are itself and 1. So the first few are 2, 3, 5, 7, 11, 13, 17, and so on. You probably recognize these. So the first result that we're going to make use of without proof is Euclid's lemma. This tells us that if we have a prime number p that divides a product of two integers ab, then you can conclude that p has to either divide a or b. This doesn't necessarily work if p is not a prime. So for example, if p was 6, which is not prime, we can show that 6 divides 15 times 2, i.e. 6 goes into 30, but that doesn't mean that 6 divides 15 or that 6 divides 2. It only works if p is a prime. Okay, the next result about primes that's important is the fundamental theorem of arithmetic, and this gives us the justification for prime factorizations, which you've probably met before. This says that every integer greater than 1 is either a prime number or it's a product of prime numbers. And we looked at that, the existence part of that in our induction video. So this product is unique up to reordering. That means if I write down two different prime factorizations of my number, then if I just shuffle the factors around, I can rearrange them to be the same. And we often write down our prime factorizations in ascending order, so to kind of have a canonical way of saying it. So that means that it makes sense to talk about the prime factorization of a positive integer. So let's just take one. We'll take 588. Now, you can break this down into 2 times 2 times 3 times 7 times 7. That's the prime factorization of that number. And the uniqueness part about the theorem says any other prime factorization will just be those 5 prime numbers shuffled around in a different order. Okay, now the last thing we want to do is to look at the one more term, which is the lowest common multiple of two non-zero integers a and b. So this is, or the least common multiple. You can say whichever one you want. This is defined to be the least common multiple of a and b is the smallest positive integer that is a multiple of both a and b. So we write this as LCM of a and b. Now it's possible to show that any other common multiple of a and b you can come up with has to be a multiple of the LCM of a and b. So let's just do one example to show what the LCM of a pair of numbers is. So if my two numbers were 12 and 18, the lowest common multiple of 12 and 18 is equal to 36. Now I kind of just did that by inspection because I can see that 3 12s are 36 and 2 18s are 36, and I can't think of a smaller number. But you can actually get that by taking the product of the numbers and dividing by their GCD. So you can see that's going to be 12 times 18 divided by the GCD, which is divided by 6. And that will once again give you 2 18s, which is 36. And again, you just need to do a little bit of an adjustment if you want to be able to use negative numbers with that result there. Okay, so we've covered off quite a few ideas about integers, and we'll be making a lot of use of these as we go through the course. Particularly things like the linear combination GCD property and the division algorithm. We'll pull these in time and time again as we go through different proofs of different things. But we'll leave it here for today. We'll see you in the next one. Ka kite anō.